Hi, welcome to Apache Hadoop 3.0 course. I'm Abhishek Sakuja from UpDegree, and in this video we are going to take a look what is the need for Hadoop 3.0. So, is it really that we need the next generation? Whatever we have seen in 2x, which is actually covering with all the issues of 1x, do we really think that there is the 2x features are not enough for the business requirement? Or do we think that Hadoop 3x is going to overweigh the features of 2x? Let's take a look in the next slide. So this is what you can see over here. We are going to do a little bit simple comparison over here, and in the later on we are actually going to go and talk about each of these sections, that how they differ in 2x and 3x. So as starting from, let's start from the top rather than from the bottom. So first of all, like we have seen in 2x, when we are talking about the architecture, we have one active and one standby node. What about if both the machines are down? Definitely your cluster is down. You do not have any accessibility for that. Although in 2x you have a federation concept, name node federation, but when we talk about high availability, there is one active and one standby. So with the 3x, which overweighs all these features of 2x, we can see that there is one active node and multiple standby nodes. So if one standby node goes down, even with your active, you still have other standby node giving you the high availability. On the left hand side, again with 2x, you can see that we have a replication factor, which means that the data get copied 3 times, of course, which means that you have 200 times the 200 percentage, not the times, is the overhead of the storage that you're going to get. And then in 3x, they have added, the Apache has added error show coding, which actually reduces this storage overhead. And later on, we are going to see, when we're going to talk about these motivations and features of 3x, in that we will understand that what exactly error show coding would mean. Then in 2x, we have Intra-Datanode Balancer, which means that, if you are storing a data in a data node, right, and let's say there are 10 different data nodes are, then we add, let's say we add 2 more nodes. So what will happen if I want to do a balancing of my data on all the 12 nodes? It's very easy. I just run the balancer in Hadoop and it just balances the data. But what about if I have 3 disks on each the machine, I do not want to add a new node for the data storage. I want to add another disk. The Intra-Datanode Balancer is not available, and at that point of time, I need to take the data manually from one of the disks and then copy it to another disk. So that was a manual task, and nobody liked to do that because it may lead to some of the corruptions. I actually personally did that once. Right, so it's a very tedious task, but with 3x it has been solved, which says that Intra-Datanode Balancer is available. With 2x, we have restricted service to Linux ephemeral ports, which means that there is some restricted ephemeral ports which we cannot use. But with 3x, there is no limitation. Java 7 is almost dead, and it's the support will also end. So therefore, the minimum Java requirement was with 2x, but now with 3x, we have Java 8 requirement. 2x was already supporting S3, it was supporting your blob storage of Azure on the cloud service provider, but with 3x we have ADLS support. Although yeah, ADLS support was still there in 2x, but not very compatible support. But with 3x we have a very good support for ADLS. Even with for Alibaba Cloud, there is a support has been added with 3x. So that's what we have in this video, and in next video we are going to cover up the motivation of Hadoop 3x. Thank you. Hi, welcome to Apache Hadoop 3x course. I'm Abhishek Sakuja from UpDegree, and in this video we are going to take a look at motivation to Hadoop 3x. So what are the real motivations? We have already seen in the previous session where I was talking about Java 7 and Java 8 between 2x and 3x. So 2x was supporting Java 7, but Java 7 has already came to an end of its life. That was announced in April 2015, and we are talking about 4 years back. So you can think that there are lots of things happening with the Java 8, and if you're not going to a new version of Hadoop, definitely all the application will not be supported with Java 7. So that's the one of the reason. So new Java libraries now only supports Java 8, and Hadoop 3x has a minimum requirement. That's what is overcoming. That minimum requirement has been Java 8. Runtime version of Java 8 for Hadoop jars. users using Java 7 can have to actually upgrade to Java 8. This is the most differentiating factor if we talk about between 2x and 3x, which is your error sure coding. So let's understand what exactly an error sure coding is all about. This is nothing new, or I would say this is not just because of Hadoop 3x this technology has come up. No, it is already there, but people were not aware because this was not attached to the big data hype, right? So now it has been with Hadoop 3x, and therefore, like people started knowing about what exactly error sure coding is. So there are three main functionality. Some of you may have already heard about a RAID, which is redundant array of inexpensive disk or redundant array of independent disk. So this is based on the same, which is which we have error sure coding over there, and the same has been implemented on Hadoop 3x. So there are three main functionality: striping, parity, and error recovery. Let's understand through this diagram that what exactly all these functionality means. But what is a RAID is all about. First of all, the RAID is like you have a disk. A single disk will be divided into multiple parts, and then the disk data is also being backed up in another disk. The same, as you see that the same happens with within the replication factor, but here it is a little bit different. Let's see with the functionality of how it is different. So we have over here a file that we are going to store on these disks. They will be first striped. Striping is equivalent to what we see that the data is stored in the form of blocks. So if a file is having 10, let's say a file is of 10 GB, right? And our block size is 128 MB, which is approximately 8 per GB, which is 80 blocks will be there for this particular file. So exactly the same, like the striping and the block works the same. So that's what the striping is. Then we have the parity blocks. So now this is a very interesting feature, right? Which is why the error sure coding is has replaced, not exactly completely replaced, but you can still use replication factor and error sure coding both in 3x. So it is the enhanced version or efficient version of not using the replication factor. Now, what is this parity is all about? Parity is, it's a kind of algorithm that has been created inside these disks with the RAID technology, that what it is exactly it is going to do. Say if we have a disk where we have block A1, block B1, also we have block A2 and block B2 on disk 2 and disk 3. But if you observe that if block A1 is in disk 1, block A2 is on disk 2, what do we have in disk 3 for A? That is AP, which is a parity cell, right? So what it do, it takes the data from block A and block A1 and block A2 and creates a parity in another disk for it. So this is how the algorithm will work to convert into a parity. Now you have a parity cell, which is a kind of mix of the data that you have in block A and block 2 and converting into code which will be recovered based on CPU power. Like, because this when you try to recover a parity, of course it needs to be translated into an actual data, and therefore these are CPU intensive jobs to convert into a parity and reading out of the parity. So how does it recover? Let's say on the second side you can see there is an error recovery. Let's say we missed out, or our block A1 got corrupted, and here we have block C2 got corrupted. So therefore what the mechanism will do, it will take for recovering the A1, it will take the block A2 along with block AP, because the parity cell contains the data from both A1 and A2 in a more efficient manner. So A2 will mix with this parity, and therefore the A1 will be recovered, and similarly the CP will be joining with the C1 block, and therefore they will be able to recover the C2. So this is how the RAID functionality works and the error sure coding. So the block recovery is done using a data cells, which is in the actual blocks, and also with the parity cells, which is in the parity block. So this will, what it will do, it will help you to reduce your data and see that how it actually helps in reducing the overhead, storage overhead. This theory, what we are going to have in the Hadoop 3x, the algorithm is based on Reed-Solomon theory, right? That's what the Reed-Solomon has created, this theory to create the parity cells. And this theory also defines that what is the best practice to see that how many parity cells will be there along with the number of blocks. And there are some more theories also, or some more algorithms which you can read on, but the most important that we are going to use in 3x, not the most important, but the only that we are going to use in 3x is Reed-Solomon theory. Let's understand with an example. On the top, you can see that we have a replication factor in Hadoop 2x. So this is how the replication factor works. We have 3 blocks, and 3 blocks get replicated 2 more times, which is a 200% overhead. So therefore 3 into 3, that's 9 total replicas. 9 divided by 3, that's what 200 overhead that you get. Let's see how the erasure coding reduces these efforts. In the erasure coding, you can see we have 3 blocks with 2 parity, and here we have 10 blocks with 4 parity. But how do we decide this, how many number of blocks we need, how many parity blocks do we need? No, you don't have to decide. There's a best practice to use, which is a Reed-Solomon theory, and Reed-Solomon suggests that we can use 3-2, which is 3 blocks with 2 parity cells, or there is another one which is a 6-3, which means you use, when you're using 6 blocks, you use 3 different parity cells for that, and when you're using 10, you can use 4 parity cells. So in this way, what you do, if you are storing 3 blocks, you do not really need to store 2 more copies of it. You just create 2 parity blocks for those 3 data blocks. So the total replicas are 5 rather than 9 in the previous code, in the previous example. So now the overhead has been reduced from 200% to 67 if we divide 5 divided by the actual number of blocks that we have, so which is 3. So it is 67% is the only overhead that we are using for the backup of the blocks. Similarly, if we go higher, the overhead reduces. How it reduces? So if we have 10 blocks, now those 10 blocks will be converted into just 4 parity blocks. So therefore, the total number of replicas that we have means, or you just say total number of copies that we have for the blocks is 14. So 14 divided by the number of blocks is 10. So the total overhead is just 40%. So you can see that from 200% we come down to 40, and that's the highest Reed-Solomon that you can use, which is 10 to 4. Okay. Now this is how the reconstruction work based on the Reed-Solomon 3:2 algorithm theory. Right, say again we have 3 blocks, which is a file called foo.csv, and we create 2 parity cells based on the theory. Let's say one of the block fails, which is B3. So how does it recover? It takes the 2 remaining blocks from B1 and B2, and for the third it will read one of the parity block and try to recover the B3, and this is how your B3 get recovered. But remember that when you do this, it is a highly CPU intensive job, because to convert into a parity, of course your CPU will be utilized, and when you're converting from parity to again to block, again it will just try to translate all the data to recover the block, which is a CPU intensive job. What are the benefits of erasure coding? Of course, we get improved HDFS storage efficiency, because we are reducing the overhead from 200% to 40%. Here we have support for multi-erasure coding policies, as I already told you that I gave an example of Reed-Solomon 3:2, 6:3, and 10 to 4. So you can just always add to understand that how many copies you are going to have. So 3 plus 2 is 5, 6 plus 3 is 9, and 10 plus 4 is 14. High blocks fault tolerance means you can have 4 failures when you go with the Reed-Solomon 10.4. Why 4 failures? Because if all 4 parity cells are gone, then sorry, you cannot recover the data. Missing block reconstruction from remaining blocks, that's what we have seen in the example. Massive development given by the Hadoop community. So there are recent developments are going on, newer versions are coming up. So, but this is an ideal solution for moreover like an archival and cold storage. As you know that when we talk about data lakes, Hadoop data lakes, that is more over your archival that you try to do. This archival is not something which you are not going to read, but you are going to read it quickly. But understand, you need the CPU power to always translate this job. So therefore, it is more more an ideal solution called as archival and cold storage. So what are the implications? File data is striped, as we already know. That's normal with Hadoop, so I would not consider as a much big implication over here. Read and writes are remote and cross rack. So again, Hadoop has been doing this for a long time, so not a major implication. So this is the one. Reconstruction is network intensive and your CPU intensive, because yes, parity cell has to be converted, then they talk about to each other, so it becomes network and CPU intensive. Better for archival and cold storage. The replication factor is for normal storage, but when we come to the parity and parity blocks, then it is better for archival and cold storage. So that is another implication that we have with erasure coding. And of course, all the tech people, they love what's going on new in the market. So there was nothing, branded after, Hadoop 2x was branched in 2011, and it was released in 2013, where all the major releases came in. And after that, they were coming with the minor releases. But for a long time, there was a very silent in Hadoop world about the releases. So of course there was a 5 years of waiting to get a new major release, and now we have overcoming 10,000 nodes benchmark on clusters. There are very few companies who actually go up to that level, so but people are always interested to know what's new in that. So improvement and bug fixing over 2x, which we have already seen that erasure coding has there to reduce the storage overhead, the Java, and later on in the features we are going to see some more features, which is like Intra-Datanode Balancer, or what are the ephemeral ports that has been now been leveraged in 3x. Okay, so that's what we have in this video, and in the next video we are going to take a look on features of Hadoop 3x. Thank you. Hi, welcome to Apache Hadoop 3x course. I'm Abhishek Sakhuja from UpDegree, and in this video we are going to take a look at the features of Hadoop 3x. So let's see what are the major improvements has been done on Hadoop 3x over 2x. So first, I know that most of you are may not be aware about history server, because we haven't gone through in deep to talk about this history server, but let me give you a quick example over here that what exactly the history server is all about. When it's in Yarn, which is the 2x, first of all, we were having a history server over there. So what it does, it just keeps the history of the application that you are running, that how the data needs to be logged when you means the data of your application needs to be logged. That is done through the history server. So how does it work? So you have a resource manager. The resource manager give the data to job history server, and it is stored in HDFS, and node manager reads from there. But it was changing. So what they did, first of all, they launched timeline server version 1, right? So there the resource manager was able to leverage not only the job history server, but it was able to leverage the Spark history servers, any other application that you are running, that history, their history server, their application history servers as well. So in that way, the resource manager get more capability to know about the other applications. But then finally with 3x, they came up with Yarn Timeline Server version 2, and this is much more interactive, much more, and this also has a visualization features, so it becomes really, I think it's a very good add-on that they have put. So here what you have, you not only take the resource manager will not only give the data to the website where you can see all these application data, but we have a separate application timeline service which has a storage on HBase, and that from there also the visualization for the application can be done. So the new timeline server has the following features, like it is more scalable, reliable than the previous version. Usability by introducing the flows and aggregation, so you can see that what is the current flow completely, the top to bottom approach or bottom to top approach, and there you will also able to do the aggregation related to the history that you have for the application, and HBase becomes the default storage rather than HDFS. Increase high availability, fault tolerance, as in the previous sessions when we are talking about the difference between Hadoop 2x and 3x. There we just try to understand that how 2x and 3x majorly differs in the high availability section. So in 2x we have one active and one standby node. If this active goes down, we have a standby available there. So we have a kind of high availability but a lower fault tolerance with just one node failure. If both name node fails, your cluster is down. You cannot recover it. You have to manually fix the machines, and then only your cluster will be recovered. And there is lots of problem in doing that. With Hadoop 3x, we have one active node, so you can see that one active node over here, but you can have multiple standby node, which is given as a passive nodes. Earlier, when we are taking the architecture overview that in 2x how the high availability works, there we are using 3 general nodes, but you can use now 5 general nodes because you have more name nodes. So the architecture would be a little bit more complex, but this is more sufficient or efficient with high fault tolerance in 3x. Changes in Hadoop default ports, as I already told you that in Hadoop 2x we are liable to use the ephemeral ports, right? So we cannot change them. There is no way that we can go inside and come out of the ephemeral port, which is 32768 to 61000. So therefore the port were almost fixed, like 50070 for name node HTTP UI, then name node HTTPS is 50. Secondary name node is the same, which is 50, starting with data node, HDFS, all those things, whatever the service that we have was related to the Linux ephemeral port. But thanks to 3x, that has been removed, because now you can have the ephemeral port of your choice out of that range. So we can really go ahead and change them. Intra-Datanode Balancer. So this is the example. Let's say we have 2 data nodes, and how this balancing would work in 2x. So if as I already told you, if you are adding more data nodes, the balancer would not give you any issue, because it's a inter-datanode balancer and you can just balance your data on newly added nodes. But what happens if you add a disk, right? If say about like you have added a new disk, you can see that the lower amount of data gets stored on that particular disk. So if the disk was there from initial stage, and then you have disk 2, which is like coming after some time, and then you have disk 3, which was later on added after a couple of months. So you can see that the amount of blocks that are getting stored on these disks is not balanced. After some time, what will happen? The disk 1 will be 100%, and you may receive your data node may get failed, right? But with 3x, this thing changed. What you do, if you want to add a disk, just add it and run this intra-node balancer, and the data get distributed on each of the nodes, on each of the disks equally. So that is the benefit of this intra-datanode balancer, where the distribution issue between the disk within the node is fixed. So we have improved Yarn UI now. This is what you can see, that this is the UI that we were using earlier, which is very straightforward. Looks like, a very basic kind of UI where you just click the buttons and it will just give you the information. That's it. But now if you see, we have a better Yarn UI, which is built on Node.js and Ember, and which is you can see the memory, CPU, queue, heat maps, and also which is your app timeline server version 2 is integrated with this. So you can see the lineages, that how exactly the work is flowing. So it's really improved version for Yarn. Thank you so much. Hi, welcome to Apache Hadoop 3x course. I'm Abhishek Sakuja from UpDegree, and in this video we are going to take a look what are the other improvements that we can see in Hadoop 3x. So the first point, you can see that it's given as a rewritten shell script. Now people who has already worked on Hadoop 1x or 2x, they may know that when you try to start any of the services from Apache Hadoop side, so in there you have to write a full command. For example, hadoop-daemon.sh start name node or start data node. In that, what we're doing, we're actually kicking off a shell script. So that is not a right way of starting the services when we talk about a production environment or a stable environment. So therefore, with this new within the Hadoop 3x, they have rewritten this shell script so that all those services can be daemonized. For example, now you can write hdfs-daemon start name node. So it will start the name node service. So you do not really need to go into the bin and take a .sh file and then try to start the daemon. However, if you go to the distributions like Hortonworks and Cloudera, so there you do not need to start the services like with a shell script. There you can just go and start it as a service. But we are talking about the Apache Hadoop itself. So this is now they have rewritten those shell scripts. Compilation and runtime scope within single jar. Now what happens sometimes, say about like you have a client, right? Client applications, and then you have an runtime application. So there was a problem, matching these two types of different client jars. One is like the client APIs, another one is a client runtime. Normally this happens when you try to interact with the third-party applications or in any other ecosystem applications. There you develop something in Hadoop and then you try to run on the edge base, then you have to write the dependency between them. So then these scope of compilation and runtime, definitely they're trying to conflict, and this has been resolved in 3x. So compilation and runtime scope within single client jar. You don't have two separate jar, one for client API, another one for client runtime. The third point is quite interesting over here, which talks about opportunistic containers in central RM and distributed scheduler. Normally we know that according to the architectures, whenever a job is get executed, we set to have the containers within the node managers, and the containers are the set of resources for the job that they need to execute. But sometimes it happens that once the job is completed, there is a time when another job is not been executed on that particular node, so that node becomes idle. What now you can do is, because you are not actually going to do it, you need to set the configuration that to launch these opportunistic containers. These are not a guaranteed resource containers which will which is going to sit inside the node manager and it's going to wait if there is any opportunity for them to take the resources from that node and run any kind of execution or the task that has been assigned. If there is a guaranteed container is coming, then these opportunistic containers will be dropped. So this is a quite interesting features that they have added in Hadoop 3x. Map output collector in MapReduce for task level native optimization. So this is a kind of optimization that they have implemented in Hadoop 3x, where just after the map output, of course, we know that there is a process of shuffling on sorting the data. Now, how about if have everything at a native code of a map output, right? So what it will do, it will have all the process within the native code just after the map output, and that will help you to sort and shuffle your your data quickly and efficiently. However, the merge is still not done. The merge is still in process, and once it is done, I think it will be available in further releases of Hadoop 3x. Support for more cloud connectors. Earlier, the Hadoop was gave a support for S3 of AWS, the blob services of Azure. Although there was a kind of support for Microsoft Azure Data Lake, but now it has been officially released that Microsoft Azure Data Lake is supported with the Hadoop 3x and also the Alien Object Storage System. So this is the Alibaba Cloud Services, which is again getting a lot of popularity in the market, and that is also now the one of the storage connector on Hadoop 3x. Support for consistency on Amazon S3 using sguard. Whenever you talk about object storage on cloud, the consistency is one of the real issue. Why? Because when you try to store the data on the cloud storage has lots of backups of that data. The consistency is eventually that you try to get on that storage, because it has to be copied from two different locations. Say about like if you were trying to read a data from S3 and it is not read from the primary location, it has to read from other location, then definitely the data has to be copied there. So until unless it is completely consistently available, of course you will not get the latest data over there. So the consistency is quite a problem with the cloud storage, but this has been resolved with the consistency support on Amazon S3, but just on Amazon S3 using S3 guard, which will make sure that you have the consistency right on the Amazon S3. Simplification of configuration of map and reduce task heap size. People who have already worked on configuration management for MapReduce, they must have known the difference that currently means with 2x, we had to set two types of properties. One is for memory, another one which is your Java heap, another one is for the actual memory that has been used to process the data. But now what you can do, you can just set one property, that's a memory.mb, and the ratio will be automatically taken to run within the heap sizes. So you do not really need to worry about setting the two properties now. Yarn federation to solve scalability issue. As we have already seen in the previous videos, Hadoop 1x having node cluster, like it can have a cluster support for 4096 nodes, and then the Hadoop 2x was having a support for 10,000 node, but with 3x there is no limitation for now, right? Why? Because Yarn has become a federated cluster. Now, what is a federated clusters? You can create subcluster within your large cluster, and the Yarn is going to manage them. Now, this is a very, I would say again, an interesting feature. Why? Because you will have more clusters than before, more subclusters, but as an organization, it will serve as a single cluster. So you have federated subcluster that will, you can add more nodes to those subclusters and distribute your jobs on multi-clusters, and just keep adding the nodes. So 10,000 limited, which you can see in Hadoop 2x, it's not available with 3x now. It's an unlimited for now. Can leverage GPU, which is your graphical processing unit, means not only CPU, because initial design was Hadoop to use a single core on a machine, which is nowadays we don't have anywhere. It's multi-cores with quad cores, octa cores, support for running an application. Along with that, they have, now we can do a GPU processing and the FPGA capabilities. FPGA is a field programmable gateway array, which try to convert your data or uncompress your data with a very wire speed of all the gateway arrays that it is going to use. So it is a very, very classic example that has been used on the data warehouse of big brands like IBM use FPGA in their Netezza so that they can do the uncompression of the data at a wire speed. So these are the improvements that we have, other improvements that we have on Hadoop 3x, and in the next video we are going to do a lab. So thank you.